Okay, we're going to continue with chapter 7, and this is going to comprise lecture 6. There's going to be one lecture or chapter difference between the series of lectures and chapter numbers, because we have covered chapter 1 and 6 in the first lecture. And chapter 7, starting from this chapter, we are going to be basically talking about statistics. And statistics, when I start talking about statistics, I mean inferential statistics, because we talked about descriptive statistics, which is kind of less formal statistics compared to inferential statistics in the very first lecture. And in those lectures, I also gave a hint about the concept of population. I said that a population consists of possibly an infinite or sometimes finite number of elements. So all the possible elements of a set or observations that can be obtained from a set, and a sample is a subset of that population. And we try to describe those samples in the first lecture using the methods called descriptive statistics. Then starting from lecture 2 to lecture 6, lecture 5, including lecture 5, we talked about properties of distributions. And although I haven't used the term population, actually those distributions are used to model populations. So this part within dashed lines, because I use these dashed lines to show that there may be infinite or maybe finite observations here. And the distributions that we have covered, for instance, binomial distribution, Bernoulli distribution, or a normal distribution, is used as a mathematical model, as a mathematical entity to describe this population, which possibly consists of infinite number of elements. Now, in reality, what we obtain is a sample, is a subset from this population. So, since from chapter 2 to chapter 5, distributions are descriptions of these populations. And in the very first lecture, we talked about how to describe samples. Here is now the very crucial point to connect these two. Since in real life, we are only going to be able to obtain samples, because although in chapters, again, 2 to 5, we talked about, I've given examples like this, given that probability of P is equal to something, that parameter is something. Or in some other questions, I said that this rate parameter of a Poisson process is something. Or given that mu is equal to something, variance is equal to something of a Gaussian process, find x smaller than whatever probability. Those were the type of questions. Now, the very important point are, these are population properties. And in real life, unless we have some theoretical good reasoning, like for instance, when you throw a dice, there is a probability of 1/6 for each face, which comes from the classical interpretation. If this is what we call fair dice, you can assign this probability. But if we are talking about a more complicated case, for instance, those areas of different surfaces may not be identical to each other, then assigning probability to each side of this dice might be difficult. Then the thing is that each side is going to have its own probability mass function value, which can be shown as probability mass function of x when a dice is equal to 1, 2, whatever. How can you find these values? So these are not that are going to be population parameters, right? These population parameters, but in real life, usually we would not be knowing these population parameters. And what you can do is only obtain a finite sample from that population. For instance, you may throw this dice 1,000 times, and then you are going to obtain a distribution. But note that it's going to be distribution of those 1,000 times. It's not going to be the probability mass function of the population exactly. So here is the question: is there a way to estimate these population parameters using samples? This is basically what this and the following chapters that we are going to be covering, and that's exactly what inferential statistics is. Going from sample to population, and this is something we have not covered yet. The mathematics will be very similar. That's why if you don't understand the concepts that I'm talking about in this chapter, you can still, without understanding what's going on, you can still do the arithmetics here, because as I said, the arithmetics will be very similar to what we have done previously. We are going to be using the same techniques, the same methods, but on the other hand, I highly recommend you to understand this chapter because it's going to form the fundamentals of statistics. So when it comes to going from sample to population, usually this is called statistical inference, and statistical inference are usually is comprised of parameter estimation, which we are going to be talking about in this lecture and also in the next lecture. And following those lectures, there's going to be a hypothesis testing approach, which is pretty much interesting, I may say. They are going to be very similar here. The methods may be different, the perspective may be different, but actually they try to answer the same fundamental question. But we are going to be approaching the statistical inference concept, which is going from sample to population using these two techniques. So let's see, what is estimation? Well, when it comes to estimation, first I'm going to be talking about point estimation. Okay. This is basically a reasonable value of a population parameter estimated using a sample. Actually, this first statement is a summary of this route here. We are going from sample to population. And why do we follow this route? Because at the end, we would like to estimate a population parameter. What do I mean by a population parameter? We had distributions up to this point. For instance, we had the Bernoulli binomial distribution, Bernoulli distribution. Bernoulli distribution has the parameter P. Binomial distribution has the parameter N and P. Geometric distribution has the parameter P. Poisson distribution has the parameter lambda. Exponential distribution again has the parameter lambda. Then you had uniform distribution with at A and B parameters, right? If this is a discrete one, and if between A and B you have the increments are one by one, and what else? And the most important of normal Gaussian distribution, which is mu and sigma square. So when you assume that your population belongs to any of those distributions, you have to find this or determine, you have to estimate these parameter values. And these parameter values are, unfortunately, although in the previous questions I have given those directly, in real life, we never know these. For most cases, do not know these parameter values. We have to estimate from samples. And here, actually, I said something, let me emphasize that. I said that we assume that population belongs or is described by any of these or by other distributions. There are other distributions that we haven't talked about yet. If you look in your textbook, you are going to see a couple of more distributions, hypergeometric. There is Erlang distribution, there is gamma distribution, there are many more distributions. And it's not always the case that your population need to be shown by these finite distributions. It may be much more complicated. It may be a mixture of those distributions. But anyway, if you are talking about a simple population, that I may say, let's say that it can be modeled by any of these distributions. The question is, how can we guarantee that some population is modeled by any of the distribution at end, or I know? Actually, I cannot guarantee that. The very first step is using our experience or heuristics. We first assume that a population is described by a distribution that we know. For instance, we may assume that it's normally distributed. But note that we use our experience and prior knowledge. For instance, if the population consists of a random variable with discrete values, then quite possibly normal distribution is not the correct distribution, right? Because normal distribution explains or models a continuous random variable. And once you do the calculations, then you check whether your assumption related with the population is described by this distribution is valid or not. This is something we are not going to very much consider within the scope of this course. We are just going to mention later in the second semester in the unit operations laboratory course. I'm going to be talking about more about that subject. But again, this is a very important issue in statistics. So we have to assume that our population is described by a certain distribution. You start with that approach. That distribution, whether valid is or not, then you do some calculations. We are going to talk about that. Then you check whether your assumption is satisfied. So in time is equal to 0, you would never know that your population can be exactly described by a certain probability. That's your mass function. Okay, let's say that we start assuming with a probability density function, a convenient, useful probability density function, I may say. Then what we need are those parameters. Those parameters are going to be determined, not, let me put, determined is a very strong word, let me put it that way, are going to be estimated using our samples. Now here is a very important point. Let's say that this is really, we know that it's normal distributed with mu and sigma square parameters, but we do not know these values. Either believe it or not, we will never obtain the exact values of these population parameters. The best that you can do is by taking a large sample, let's say, as large as you can. It is possible, and in some cases it may not be possible to obtain a sample with a large sample size. Anyway, you have to estimate these values. So it's going to be always estimation procedure from sample to population. All right. So how is this estimation achieved? What we do is we collect a sample of observations. Note that a sample corresponds to all that set of n observations. Each one is an individual observation. This whole set is called a sample. Let's recall those from the very first lecture. Now, n observation, what's going to be n equal to? It depends on the process. It depends on the sampling procedures. We'll talk about that later. Now, the important thing, and it's the first time we are going to be using the term statistic in this meaning. So in lecture 1, we talked about the definition of statistic was given as a collection of data and graphs and lists such that it's going to explain the whole data, all the properties of the data for humans. That's basically what statistics is. So it's actually you collect the data, you use some methods, graphical methods or numerical methods to be able to analyze the data in easier terms for human mind to have a better grasp of that data. That was basically what statistics is. Statistic is, and actually that's, or the plural form statistics is, and that's usually the one which is used in daily life. If you are talking about statistics, or if you talk, if you ask somebody what statistics is, who has got no idea about, who has never taken a formal course about that, he or she will try to explain you probably in terms of that. He or she is going to talk about probably some plots, bar plots, maybe he or she would not, of course, say the formal term of bar plots or histograms, but probably that's what it means. All right, now the more formal definition of, or in singular form, there is a definition of statistic. A statistic is, and actually that's due to Ronald Fisher, a statistic is any function of observations in a random sample. That's a very interesting term. Actually, when I say it says any function, it means any function. What do I mean by that? Let's say this is our sample. You can come up with any function that you like. What are possible functions that you can use? For instance, this may be a function. Find the maximum value. Call this, for instance, S. Maximum value of S is going to be my statistic. call it my stat. Call it my stat 1. This is going to be my stat 1. Take a sample, find its maximum value. Or rank order them, take the second term and take the fifth term and divide it by 3. This is going to be my stat 2. Now you may ask the question, or probably this gets easier to understand, or my stat 3, a third one, is sum all these values and take the square root. So the question that probably pops up in your mind is, okay, but what is the use of that? I'll come to that in a minute. But first of all, let's understand the idea that any function of a random variable, of the individual observations that random variable, and note that you don't need to use all of them. This maximum means it's going to be only the largest value. This one means only the rank ordered one, the second and the fifth one they are used, and here all of them are used. What is the use of that? I'll come to that in a minute. Or can we use any? Yes, you can suggest any statistic. But being an estimator is a different story. Now, once you suggest, and that's why it says appropriate statistic. If it's an appropriate statistic, it can be used to estimate a population parameter. So therefore, statistic becomes an estimator. That you can describe any function, you can use a function, but that won't be an estimator. In order to have a good estimator, your statistic should be appropriate, right? So it should be able to estimate a population parameter. So that's what we have here. In other terms, in more formal terms, be patient in for a couple of more minutes, it's going to be clear. We are going to have what we call a population parameter. We are going to show it with theta. This is also called parameter of interest. For instance, if we are talking about, you assume that some random variable is normal distributed, then we are going to be interested in estimating mu and sigma square, because these are the population parameters of normal distribution. So these are parameters of interest. The question is, when you have a sample, this is a population, and when you obtain a sample, and when you apply a statistic on that sample, what are the appropriate statistics so that you are going to be obtaining estimations of these population parameters? Now comes the second concept, point estimator. This is shown by a theta, but this is slightly longer. At least that's how I try to show it. In your textbook, this is more like a thick kind of horizontal line. That's the best that I can do. And note that there is a hat here. When it comes to estimations and predictions, there's going to be always that, or for most cases, it's going to be that hat is going to be added to the parameter. So when you see a hat, it means that I'm not talking about the parameter itself, I'm talking about its estimated or predicted value. So point estimator, and please pay attention to the word estimator, is the statistic used to estimate data. So we are using a certain function, and here's, for instance, this is the function that, let's say, I'm talking about, maximum value of S. Or let's come into more friendly waters, I may say. This can be a very nice statistic. At n values, divide by n what we call sample mean. Is it a statistic? Yes, it is, because this, as you can see, is supposed to be this is a function of xi values, sample values, therefore it's a statistic. Now, can we use it as a point estimator? I'll come to that, and the answer is yes, it's a very good point estimator, and this is going to be used to estimate mu. So how did we get from the point estimator of Xbar to mu? I'll come to that. Actually, the whole chapter will be about that. In each part, I'm going to put a small brick to build the whole wall to explain the whole concept. I hope so. All right. So the point estimator is the statistic that we use. That's going to be used as an estimator. And note that we have also what we call point estimate. This is the specific value obtained by this point estimator. So this is just like the difference of the random variable x and the specific value random variable takes. So it's the same value, same relation here. Now you may ask, is this a random variable point estimator? Yes, it is, but I'll come to that in a couple of minutes. So let's try to show the whole thing on an example. For instance, if we are interested in a population mean, to estimate mean, then theta is going to be population mean. Theta with horizontal, long horizontal line is going to be, for instance, this may be sample mean. In other cases, this may be median, or it may be also mode. I'll talk about these in a couple of minutes, or in, maybe in the next lecture. So within that series of lectures. So let's, for the time, without any proof, we can use sample mean as a statistic, but not only as a statistic. This is, you don't need proof for that, because sample mean is a function of sample individual values, but this can be also used as an estimator. And the specific value that the sample mean takes, which is shown with a lowercase x bar, is going to be theta hat. Here, actually, I don't show this with a long horizontal line. This is the typical theta. So you may easily say that this is the population mean and this is the population mean estimate. You can also write it that way. So population mean estimate is going to be a particular value of sample mean. But note that this is not the case. It doesn't mean mu is equal to x bar. This is incorrect. We will never know what mu is. The best that we can come up with is mu hat value. So as an example, if x is, for instance, let's assume that, actually we don't need to assume anything right now. We don't need to assume anything about distribution. If, let's say, from a process, we take a sample of 4 observations, and that process, we call it a population. It has a mean value, and we would like to estimate this mean value. So taking a sample of 4 elements, you find the sample mean as 28.75. This is actually a point estimate of population mean. Note that this is point estimate. And here, please pay attention to the word point, because we are talking about a single parameter here. That's why it's called a point estimate. Later, we are going to talk about something called interval estimate. So the point estimate, which is this one, is equal to the specific values, 28.75, the population mean is equal to 0. Therefore, mu hat is equal to x bar, which is equal to 28.75. And here, this specific value of point estimate is found determining sample mean, which is actually the estimator. So the point estimator is the sample mean. Point estimate of the population mean is 28.75. I hope that's clear. Now comes the pretty, I feel, interesting concept. Actually, I have just gave a hint of that here. And I said here, I likened this to x and lowercase x. And I said, is this a random variable that I liken these to the relation of x and lowercase x? Random variable x and specific value of x. And the interesting answer is yes, this is a random variable. But probably it's a little bit tricky to understand the concept, so let's pay attention to that. Now, first of all, a parameter is a constant. What do I mean by that? Mu, sigma squared, p, lambda, all these values. These are functions of, for instance, mu can be found using x, fx, dx over all domain of x, or from 0 minus infinity to plus infinity. So mu depends on all the weights or all the distribution. But once it's calculated from all the values of mu, mu is a constant. So here constant means constant with respect to samples. And why do I give such a meaning? This being constant is within the perspective of the random experiment. Now, what does random experiment mean? If you go back, when you do the experiment, each time you do under identical conditions, you obtain a different sample, x1, x2, x3. Maybe individual observation, or maybe a sample consisting of different results. It doesn't matter. So x1 may consist of a single observation, or it may consist of multiple observations as a sample. It doesn't matter. But what I mean is, the property of random experiment is each time you perform the experiment, you obtain actually maybe not necessarily different result, but there may be different outcomes. And these all outcomes, as they go to infinity, is going to form the probability distribution function of x. That's basically an explanation of what we have done up to this point from chapter 1 to 6 in a nutshell, maybe. So here, from this perspective of random experiment, from experiment to experiment, mu does not change. Therefore, it's a constant. Please see the relation between those two. Although mu is a function of x, it's a function of all x values over all distribution. Hence, it's a property of the process. Hence, it's constant with respect to experimentation. This is the same thing with Q or sigma or any population parameter. So population parameter is constant. But here is the problem or interesting point. What about the point estimator or its point estimator? And what do I mean by point estimator? I'm talking about this here. Is this constant from sample to sample? Let's see that it is not. For instance, for this question, let's say that this was the sample of 4 elements, and that was actually we have used the point estimator of sample mean, and we have found the point estimate of 28.75 from these 4 observations. Now, let's say that you repeated the experiment under identical conditions, and this time you obtain these 4 x values. 26, whatever. And please note that these values are not identical to those values. Right? They are similar but not identical. Now we are again using the very same estimator, the function or the statistic. And this time when we use it here, X bar will come out to be equal to 28.25. Which is different from that value. It may be close, but that's another story. It all depends on the variance here. Whether being close or not is another story. The thing is, it's not constant. So from sample to sample, the interesting point, X bar will also change. So I'm going to call it 1, 2, 3, 4. Which means what we call the point estimator, the function itself is a random variable. So here is the dilemma. X is a random variable. Mu is not a random variable. So random variable, not random variable. And we use these X values to compute X bar so that we are going to use it for mu hat. This is the link between those two. On the other hand, these are also random variables. So the estimation of estimated value, point estimate of mu, which is X bar, is also a random variable. And this explains the whole thing. So when you have a random variable, go back to X. When you have a random variable, we had its probability density function or probability mass function, and we had its domain. And we had actually all these different distributions to describe X. Whatever we did for X is going to be applicable also for X bar. Because you can now, we have a new X in town, which is X bar. So this is supposed to have a probability density function, mass function. This is supposed to have a domain, and everything that applies for X is going to apply for X bar. So therefore, theta hat should also have a probability distribution. And this is going to be called sampling distribution. That's a specific name here. So a distribution itself usually refers to the original random variable. When we are talking about a sampling distribution, we refer to a distribution of a statistic. Basically, so let me repeat. Again, for instance, and to make it much more clear, maybe I can show it here. Let's see. All right. When you have a random variable X, a single observation, let's say, it's going to have Fx, and this is going to be the distribution of random variable X. when you apply a statistic on X, apply a statistic here. For instance, it may be X bar, X tilde, or any other statistic that we have defined previously. My stat1, for instance, if I recall correctly, we have defined this as maximum value of X. Note that from sample to sample, this will also change. And as an example, if this is our population, when you take a sample here, and let's say this X1, call it, and this is going to consist of observations X11, X12, X1, and n observations here. So a sample of n elements. A sample of n elements. So when you take X1 bar or X1 tilde median, or actually my stat, actually that's a very long name, let me make it easier. Let me call it MS. Then it's going to be MS1. These statistics will only refer to that sample. When you take another sample, here we are going to have different X2, and MS2 values. So if you take, actually, when you take an infinite of samples from that population, just like from this population, when you take infinite number of X values, you are going to obtain the distribution of X. When you take infinite number of samples comprising n elements, you are going to have all these samples which go to infinity. And you are going to have their distribution. This is going to be the distribution, probability distribution of sample mean, right? Over all values, or you may have for simple median, or you may have MSX. Note that here this is the random variable in its full form is written here, whereas usually we use the lowercase x value for any random variable. So now the question is, what is this equal to? Why am I interested in that? I'll come to that. Well, the following lectures will be all about that. But now, just for the sake of answering this question, what is going to be the probability distribution function of a statistic? Specifically, we are talking about sample mean. So what is going to be the distribution, sampling distribution? Note that these are going to be called sampling distributions, as opposed to sampling distribution. So there's a difference between those two. So what's going to be sampling distribution of X bar? This is going to be our question. And this is not that much of a novel question. Why? If we recall, we've previously talked about functions of random variables. We had, for instance, y is equal to a function of a random variable. And well, it was one of the bonus lectures which you are not responsible, but I have in that bonus lecture, I talked about, well, in the lectures that you are responsible from, you have to know how y and variance of y can be computed if expected x and variance of x are given. We already know that. But given that, or given this quantity, how this quantity is computed requires an additional information, and that was one of the bonus lectures. But basically what we are dealing with now is exactly this situation. And is this a function of x? Yes, for instance, if we have n elements, and if we are specifically talking about x bar, what we call x bar is, you can easily liken it to y. It's going to be x1 over n. So the question that we are asking is, if we know the distributions of these x values, they come from the same distribution, and usually we are going to assume that they are independent, identical distributed, can we find the distribution of y? In terms of Gaussian distribution, if you recall, in the last part of joint distributions, we talked about this concept. I'm going to link up all those stuff so that you can connect all the dots. For instance, we said that if XR, each of them is identically Gaussian distributed, or actually not, you don't need them to be identically even distributed. If they are Gaussian distributed, we said that Y is also Gaussian distributed. So this is going to be the same thing. Xbar is going to be also Gaussian distributed. But I'll come to that in a couple of minutes. So let's go back to the point presentation. All right. So let's try to solve an example. Determine the sampling distribution parameters of X, right? Well, actually, the sampling distribution parameters of X bar, I'm sorry. And X bar is defined by this fashion. Assume that Xi's are identically distributed, identically and independent distributed. Okay. And determine expected value of X bar, variance of X bar, the sampling distribution parameters. All right, let's see what's going on here. Here it says we have an X here consisting of a couple of samples, let's say X observations, of N observations. Let's try to materialize this using a scenario. Let's say that your product, your company manufactures a liquid product, liquid chemical, hourly, let's say, and each hour you take one of the bottles randomly and you measure the liquid content in it, and it's some certain value, and this is the second hour till the nth hour. And this actually, the production is a very, very long run, days, months, and you randomly selected here this part. Actually, I'll come to that point again, and I jump from topic because this whole thing, this whole part of statistics, you have to understand multiple parts simultaneously to get it done. So step-by-step procedure is not that much favorable, I may say. So in some cases, this may be all a little bit confusing from different topics all together, coming together, but try to follow. Here is the idea, taking all these samples from a certain region of, let's say, with 1 hour intervals to demonstrate or to represent this region may be going minus infinite to plus infinite time. Of course, it's not practically true. Usually it's going to be a finite time for a factory to be manufacturing a product. But anyway, this is not a very wise choice. Actually, we usually do something called random sampling. Later, we are going to be talking about. So a better procedure to represent the population would be probably randomly taking different samples from different time parts. For instance, you take a sample here for 3 months earlier than 2 months, maybe another one here, or like this, if we call this up to 0 time. So from different regions, maybe just selected randomly, we take n of these samples. And the question that we are trying to understand, first of all, the question, the ultimate question is find the mu value here, or estimate the mu value. What do I mean by the mu value? Actually, we have all these bottles here, and if you were to obtain all these bottles here, that would be the population of these bottles, right? These bottles would have a single mu parameter corresponding to the chemical amount or chemical composition in each of these bottles. It's going to be a mu value here. It's going to be a constant population parameter here. And this is population parameter is something that we do not know. What we would like to do is to estimate this value. All right, that is the ultimate aim. And in order to do that, we are going to be using sample mean. So I think that the whole thing sits well within the architecture I tried to explain at the beginning of this lecture. So using a sample mean, we would like to estimate mu value. But here the question actually only deals with the properties of Xbar. Why do I bother about dealing with properties of Xbar? Just take a sample, find the Xbar value and say that this is equal to mu n. That's over. Unfortunately, that's not over because I know that if I had taken another sample of n elements, there would be a different Xbar. This is probably not equal to, well, it may be equal, but just it's with a very small variance is due to log or log, things like that. So it's likely to be different. So what's that? Why does that bother me? Because mu is a constant value. And if I had taken another sample, I would have found a different value, which is problematic, which is the correct one. And here in terms of statistics, I need to deal with that issue and analyze the whole situation. And to analyze this, I have to analyze the distribution of Xbar. The reason why these changes, Xbar values changes, because Xbar itself is a random variable, and therefore it's going to change from random experiment to random experiment. All right, so although my aim is, as I said, to obtain this value, here for this question, I would like to understand the properties of Xbar. And understanding the properties, since Xbar is a random variable, understanding the properties of Xbar means that, well, the best way to understand is find the distribution. I'll leave that to the end because I do not know here for the distribution of X, and there's an additional topic I'll talk about. If we don't know this probability mass function, distribution function, the next thing that we can find in terms of statistical reasoning or statistical explanation is find the expected value of this statistic. Although Xbar will change from sample to sample, since it's a random variable, it's going to have an expected value. What is this equal to? And then variance of Xbar. And what's that use? What's the use of that term? It's going to tell us how much Xbar changes from sample to sample. If the change is very small and depending on this value, then I may rely on that value. Let's go step by step. So for the time being, I'm going to skip this one. I'll come to that later. Let's first deal with this issue. Note that expected value of Xbar is not a new problem that we face. It's a simple problem that we have faced before, but never within the concept, within the content of estimators or statistics. Note that I repeat again, we have dealt with this issue in terms of functions. When you think Xbar as a function, this is a problem that we have solved before. On the other hand, here, although the mathematics or arithmetics is the same, as I said previously, the approach to the problem or why we apply this mathematics is totally different. We are talking now about properties of a statistic which is going to be used as an estimator. So that's a total new topic and new issue. Try to understand this idea. So anyway, here you can take n out if I can find my cursor. And this is going to be equal to x1 plus x2, blah, blah, xn. And why can I do that? Because expectation is a linear operator. When it's a linear operator, you can apply on each of these x values. Now, what does this mean? It means in a sample, the first element that I choose, here actually I'm very sorry, these are going to be expected values. All right, the first term means expected value of x1. It means in a sample, and I'm going to be hypothetically, actually, I could have taken many of those samples. Expected value of x1 means in all those infinite samples, what is the expected value of the first element that you choose? The first element that, since we randomly choose it, it doesn't make any difference choosing the first element or the second element, third element, as long as it's random. Therefore, this is going to be equal to mu, the process expected value here. And this is going to be mu again, this is going to be mu. We have n of these mu's. Therefore, the result is a very straightforward but a very important result. Now, for those who just focus on the arithmetics here, it's not going to mean anything. It's going to be expected value of x is going x bar. I am very sorry. X bar is equal to mu. But for those who were able to follow up to this point, I think it's a very important result. We were talking about an estimator, right? Sample mean, and we didn't know about the properties and the relation of that and the relation to mu. Here this says that expected value of x bar, your statistic, your estimator, is going to be equal to mu. If you take an infinite number of samples and take the average of those x bar values of those samples, that's the one interpretation of expected value, it's going to converge to mu. And that's a very good property, because when you know that, actually, since you know that you are going to converge to mu, you can use x bar now as an estimator for mu. Up to this point, I have never validated this. Well, this is still not a validation, complete validation. I'm going to come to that later. But if your statistic, if your expected value of your statistic is equal to your parameter of interest, the parameter that you would like to estimate, then that may be not exactly, because there's more to that, I'll come to that, but that may be an indicator that x bar, or the statistic that you are talking about, may be used as an estimator for the parameter of interest. Okay, now comes the second issue. What about the variance of x? Now, if maybe somebody may naively liken this here and say that, okay, if this is the case, then this is going to be equal to sigma square. But this is not going to be the case, hopefully, because that is why we use actually averaging. Let me first do the derivation, very simple derivation, because derivation is the easier part. Understanding the result is the more tricky part. It's going to be again x1, x2 to xn over n. You take n out, 1 over n square, and variance of each of these can be written as separate terms. Am I justified in doing so? Yes, because actually the cross product terms are 0 since they are independent. So please relate them. So let me say here, plus cross products 0 since xi's are independent. Now, each of them is, due to the same reasoning I talked about before, is equal to the variance of the random variable x. We have n of these. Now, here is the very important result. So what's the big deal about this? The big deal is this. Although the x has a variance of sigma square, what does variance mean? Let's go back to the basic. It's very easy to get lost in those derivations. The spread of x is described by sigma square. On the other hand, spread of, where is my cursor? Spread of x bar is described by sigma square over n. And since n is going to be a number greater equal 1, then variance of x is going to be greater equal variance of x bar. Spread of x bar, if you have a sample size n greater than 1, and as long as it gets bigger, variance of x is going to get smaller and smaller. What does that mean? That is the very important thing I would like to talk about. Get rid of all of these. And actually, let me try to show it here on the. All right. So how can I erase the whole thing? It's difficult. So let me start with another table. The distribution of x, for instance, will be like this. Note that I have intentionally plotted a non-Gaussian, a right-skewed distribution. This might have been Gaussian, but now for the timing, I'm not talking about the distribution yet. I'm only concentrating on mean and variance values. Now here mean is going to be somewhere here, mean value. And note that why did I not show here is to the right hand side. Go back to the very first lecture and try to come up with a reasoning. Now the question is, although I don't have information, I haven't talked about the distribution of sample mean here. I'm going to just briefly talk about that, but I'll come to that in a couple of minutes. Mu is the same place here. So expected value of X is mu. Expected value of X bar is mu. They are the same expected value. Now variance is proportional to this width here, not exactly anywhere, but general distribution is proportional to that width here. Now I'm not going to show you the shape here. Actually, I cannot do that, and this is going to depend on sample size. But let me just for, if n is large enough, I may say, this is basically what you are going to obtain. Now, why does that look Gaussian? I'll come to that in a minute. I just don't care about the shape of the probability density function. It's not the point here. The real point here is the width of the distribution is now smaller. Oh, let me write it this way. Variance of, whereas variance of X is sigma square. And what's the advantage of this? The advantage is this. When you take a sample X bar here, when you take a sample and find X bar value will be determined, or will be the probability density function of X bar will behave with respect to this probability density function. And since its expected value is equal to mu, the result cannot be too distant from the mu value. On the other hand, when you obtain a single X value, although the expected value is again mu, you can be very distant here anywhere. This is the reason, and that's a very interesting point, why instead of a single observation, we usually take multiple observations or measurements and find the sample mean to come up with an estimation of population. Well, actually, in real life, in experiments, in previous experiments, in real life experiences, probably you never use the word population or population mean, but when this is something that we usually do. For instance, you repeat an experiment 3 times and then find the average value and report it. And here what you do is actually, without realizing, you think that under a certain conditions, identical conditions, your experiment has a certain mu value. This is a constant. Each time you perform the experiment, you obtain a slightly different or maybe a drastically different result. That's not the point. Here, but to come up with the best estimate of mu, you take the sample mean of those 3 and you say that this is the value that you come up with. You never use the word mean or population, but actually what you do is that one. And in daily life, there may be similar consequences. If you, let's say that you would like to run 50 meters and you would like to find the average time that it takes for you to run 50 meters, you run, let's say, 10 times, and you are going to take the average of those values. What you do is, maybe without thinking about too much, if you had run this for infinite number of times, then you would have a population mean value. By running 10 times, what you find is your average sample mean value, and you take this as an estimate of that population mean. So here is the point. Why don't you only run once and call it mu hat? Actually, in terms of expected value, that's okay. Because even if you run once, the expected value of that single run is equal to mu. The problem is the variance. In a single run, it's going to be somewhere here. It may be anywhere here, and it may be pretty much distant away from also from the mean value, population mean value. On the other hand, if you run for 10 times, this variation is going to be divided by 10. If you run for 1,000 times, it's going to be much smaller. This is going to be a much steep, or actually a spike-like object. And what's the important thing when you have a spike-like thing here? Then any value that you have obtained here in terms of Xbar, you can guarantee that it's going to be much closer to the mean value. Therefore, it's going to be a more reliable estimate of mu value. It's not only that expected value being equal to the population parameter or parameter's interest is important, but also variance of your estimator should be small. Those two conditions make up a good estimator. So for a statistic to be good, you make sure that this case is satisfied. But there is an exception to that. So, and there is, the exception is such that, although I'm not going to go into detail, most of the modern statistics and machine learning are based on estimators such as this case is not satisfied, or this is the case which is usually satisfied. That may seem strange, but that's a detail. So for the time being, a good estimator, the expected value of a good estimator is equal to its parameter of interest, and the variance is going to be small. Now a word related for the distributions. Note that the expected value and variance, this analysis works for any distribution of X. What if now this time we give, we know the distribution of X, and let's say that X is normal distributed. Then still all those relations that we have derived for expected value of Xbar and variance of Xbar will still hold, because they are going to hold for any distribution of X. But additionally, now we have the property that Xbar is a linear function of X1, X2 to Xn. Actually, let's write this in G, where G is a linear function, where G is a linear function. And if, since X, all of them are normal distributed with mu and sigma square, and X are all independent from each other, therefore this function itself, hence X bar, will also be normal distributed. That's the very important point. Therefore X bar will be normal distributed with the expected value of X bar that we have previously found out, which is equal to mu, and its variance, which is equal to sigma square. So therefore we can easily now say that the distribution of X bar is going to be, if X is normal distributed, so if the distribution of X were something like this, where it's mu and spread proportional to sigma square, the distribution of X bar would be a much narrower distribution around, again, the population mean value of mu. This is going to be proportional to sigma square over n. Depending on the sample size, it's going to be much narrower and broader, but the most broader case, if n is equal to 1, this is going to be the distribution of X bar, because if n is equal to 1, X bar is going to be equal to Xi. The sample mean is going to be the single observation, therefore we are going to have the same observation. That's why taking the sample averaging is advantageous. Now, continuing from the previous topic, where we had a sample and we would like to estimate population parameter mu using sample mean, and we have given an example that for any distribution you always obtain expected value of X sample mean is going to be equal to population mean, and the variance of sample mean is going to be equal to variance of X, so population variance divided by, and so it's going to diminish, it's going to decrease the population variance, which is a good thing. So sample mean is going to be, the distribution of sample mean is going to be less broader, but not going to be the distribution of X bar. That was the question. When X is normal distributed, that's great, X bar is going to be also normal distributed. On the other hand, if X is not normal distributed, then what's going to be the distribution of X bar? This is the question. So for any distribution of X, do we have a nice formula to determine the distribution of X bar? And note that X bar is a specific function of X1 to Xn. Actually, we can write it as X1 plus X2 plus Xn. So for this specific functional form, do we have an easy formula or something like that so that we can change the probable distribution of X to Fx bar? And why do we need that? I'll come to that. Actually, we are going to do some computations related with X bar. But just believe me that we need this. So there is the very nice theorem which is called central limit theorem, abbreviation. And that's why the normal distribution or Gaussian distribution is that much frequently observed in the universe, in the world around us. And this theorem says that if any distribution of X, if you have independent of these X values, and then as the sample size goes to infinity, then this quantity is going to be a standard normal random variable. Usually the mathematical definitions at first sight seem a little bit confusing. So practically it means this. It doesn't matter the distribution of X. It may be any distribution. A bimodal skewed distribution such as this one. If you take a large enough n value, and let's say that n goes to infinite, so you take a sample from this population, right, consisting of an infinite number of elements. Of course, we're going to relax this assumption. And then we find X bar values, sample mean. And we do it an infinite number of times. The resulting distribution of X bar, Fx bar, is going to be normal distributed. That's what it says. Around mu value, which is the mu value here, wherever the mu value here, and here the sigma is going to be sigma square over n. That's why it is standardized form is subtract from its mu and divide by standard deviation is going to be standardized normal random variable. Now, the only thing that's a little bit making this theorem not seemingly applicable is this condition. Hopefully, we can very easily relax this. If X has a probable density function close to normal, maybe not this bimodal with skewed one, but maybe close to normal or something like this. A distribution such as this one. So this is lightly, rightly, and lightly skewed distribution, let's say. This may go to infinity, or maybe it starts here, but it's not, as you can see. Of course, it's normal, especially if it's bounded. But on the other hand, it seems to be also not very much different from normal distributions, close to symmetric. For those distributions, even if you take samples size of 5 elements. So if you take randomly sample 5 elements here, 5 observations, then take the sample mean, and if you do this an infinite number of times and plot the corresponding histogram or probable density function of Fx bar, what it means is this is going to be normal distributed. That's what central limit theorem says. Although this awful normal distribution, what I draw, is going to be normal distributed. Well, if X is a probable density function severely non-normal, well, actually, this is taken from your textbook. I have come to cases where even n is, there may be such severe non-normal distributions, even n is equal to 500 may not be sufficient to realize central limit theorem, but that's okay for our purposes. If our distribution does not look like a normal distribution, for instance, such as this one. This does not look like a normal distribution. Probably, quite possibly, from this distribution, if you take samples with about 30 elements, then find the sample mean and come up with a probable density function for sample mean, it's going to be normal or close to normal. And that's the application of central limit theorem. And that's, as I said, a very fundamental and also very useful property, because irrespective of the probability density function of X, X bar will tend to a normal distribution. That's basically what it says. Okay, let's try to apply this on an example. Let's say that here actually you cannot see it because it's my picture is there, but here it says n is 40. So find the sampling distribution for X bar if X is distributed in this fashion. Note the difference between X and X bar. If you haven't understood those differences, just go back to the previous video about lecture 6A and just watch it again to try to distinguish clearly between X and X bar. X is the original random variable. X1, X bar is the statistic obtained from a sample, but both of them are random variables. So if this is the probability density function of the original variable, then if you take samples of sizes equal to 40, what is going to be the distribution of this statistic, which is going to be sample mean? This basically questions. Note that the sample size is also have to be given. So let's see. The idea is very simple, actually. First of all, let's start with the easier thing. Expected value of the statistic and variance of the statistic we are going to find. And these are irrespective of distributions. Note that we have previously found these to be equal to expected value of X, and variance is variance of X divided by N. We have previously found this in lecture 6A. Just go back and check. Expected value of X here is, now this part is a property about the original distribution. That's why these equations are very much nice. Actually, this part is a property of the statistic or estimator that we are going to be using, and this one. But the right-hand side are the probability obtained from the probability density function related to the random variable, origin random variable. So this is going to be equal to, if you have a uniform distribution between those two, it's going to be b plus a over 2. It's going to be 6 plus 4 over 2, which is going to be 5. And here we need to find variance of X. Variance of X, again from the original distribution, is going to be b minus a square over 12. Please check in your textbook or in your notes what the variance of a uniform continuous random variable is. It's going to be 5 over this one square 12. So this is going to be 6 to the power 2 over 12, which is going to be 1 over 3. Now we have expected value of X bar and variance of X, but note that it was nearly about to forget. Variance of X bar is variance of X, which is 1 over 3, divided by the sample size, which is 40. Therefore, this is going to be 1 over 120. So we have variance of X bar here and expected value of X here. That's great. Now, what about the distribution of X bar? If X were normal distributed, X bar would have been normal distributed. Since X is not normal distributed, can we do anything related with that? Yes, we can. Actually, central limit theorem says it is about this. If you have a sufficiently large sample size for any distribution of X, if each X is independent, then you are going to obtain a standardized normal distribution by this transformation. That's what it says. Hence, therefore, since actually N is equal to 40 greater than 30, and each X is independent and X are independent. I should have mentioned in the question here, but actually I think it's obvious. Since it then central limit theorem applicable, therefore X bar is normal distributed. Therefore, X bar is going to be normal distributed with the variance 5 and sigma square 1 over 120. And anything else? No, that's okay. So what this means is this. If the original distribution of X is like that. One over 2 here. Then the corresponding probability density function of X bar, but only for n is equal to 40. Note that if I said n is equal to 2 or 5, quite possibly that we wouldn't be able to use the central limit theorem, because this should be sufficiently large. All right, so the sample the mean population mean is 5. So here the same population mean is going to be here, and we are going to have a normal distribution around this population mean. And related with variance, we found related variance 1 over 20. Sigma should be equal to, I should have written here somewhere, yes, 0.091. Okay, this is going to be approximately equal to 0.1. Now I can actually show where these points are, not exactly, but approximately. So for that, I'm going to extend these points a little bit more. So it's going to be 4 is here, let's say. I want to show this as much as in scale. All right. So again, this is 4, and this is going to be 6. And this is going to be 5.1, and here this is going to be about 5.2. 4.9, 4.8. And how did I come up with these values? Actually, the part where you start to see that this Gaussian curve seems to touch the horizontal axis is somewhere here about 2 standard deviation in plus and minus direction. Since standard deviation is 0.1, please check with your textbook, and actually it's please relate it to the area inside the 2 standard deviation parts. So it's going to be plus 2 standard deviation here. It's going to be 2 times 0.1. So it's going to be 0.2. Of course, I'm talking about approximately. So plus 0.2 plus minus 0.1 around the population mean. So corresponding or comparing with the original distribution, we have shrinked and also changed the shape of the original distribution when it comes to X bar. So that's an interesting thing, and please try to absorb this idea. And the whole thing is due to central limit theorem. So how can we use this in an example? So here it says, note that X is normal distributed, though X is not. For instance, what's the probability that X bar of a sample of 40 observations will be greater than 4.90? If I had actually shown this, here it says X bar. I think it doesn't look like a very nice X bar. Anyway, so if I had asked this question for X, then I would have shown it with this. Then what I would have done would be to integrate this region. That would be the result, that for a single observation to be greater than 4.92. But it's not what is asked in this question. This is not what is asked. What is asked is find the probability that X bar of 40 observations is greater than 4.92. Now the distribution of X bar is not this distribution. This is the distribution of Fx. The distribution of X bar, as I've shown here previously in the previous slide, is this one. All right, this is supposed to be a normal distribution. Oh, it looks like a caricature. Anyway, and the X bar is, since it's normal distributed with 5 and 0.0, what was the value? 91 square. These are the mean and standard deviation values. Therefore, we are to solve this question, we need to find Z value greater than 4.92 minus 5 over 0.091. If you do that, the result is going to be probability of Z 0.08, somewhere here I have written, it's going to be minus 0.88, which is going to be equal to 1 minus cumulative distribution function value of minus 0.88. if you read this value from your textbook, right, table at in the appendix, it's going to be 0.184, and the result is going to be 0.881. So this is the value where, if I can draw it a little bit better. All right, I'm not going to draw it that much slim fashion. I'm going to draw it more broadly, but I'm going to show here 4.9 and 4.8 and 5.1 and 5.2. So the question is 4.92, yes, somewhere here. This area is asked. Please see the difference between those two. Actually, if again we can compare here. Actually, the probability is going to be just about 0.5, very little greater than 0.5. On the other hand, here the probability is very much close to 1. Why? Because the deviations from the population mean has a lower probability in sample mean distribution. That's the very important thing between a single observation and the statistic that we obtain from the sample. Now, this is actually an application. There may be many different applications of that topic, but this is an application of that topic in your textbook. And although sometimes I feel that this maybe slightly disturbs the momentum of the whole topic, still I'm going to talk about that since it's in your textbook, and I think this is an important engineering problem. Why do I call this an important engineering problem? Because in engineering and also in many things in life, we usually would like to compare two different populations. So a point estimation of a population mean is something that we usually do, but there is also another issue that we would like to estimate the difference, the deviation or the difference between two population means. Why is this the case in real life? There may be many cases where you can think of, but in engineering especially, the typical case here is you have a product by a certain method. Let's say this be a certain method or a factory which uses a certain method of formulation to come up with a product. Then you have an alternative factory or a recipe to produce the same product but with slightly different or slightly improved, or you think that it's improved product. So what you would like you to do is, whatever the quantity that you are interested in, call it here in mu2, here is, or mu1, it doesn't matter, and call this mu, let this be mu1, and call this mu2. And usually we would be interested in the difference between those two. We would like to have an estimate here, so that how much improvement, if or is there improvement between those two different recipes in production. So it's not only a single population mean estimation, but the difference between two populations. There may be other things. Of course, you may be interested in adding two populations or multiplying some population by a constant or anything, any linear combination or non-linear combination, but the specific one, difference between two populations, is a very typical case. So what we do here is this. First, actually, we don't need to start with the normal assumptions, right? Just forget about timing, again, without any distributional assumptions. What we would like to do is, we would like to estimate the different population mean, the difference in population mean of two populations. So we take samples of sizes N1 and N2 from those populations, and we come up with the sample mean values X1 bar and X2 bar. The question is, next, what are we going to do? Just like the heuristics that we use, that Xbar may be an estimate of mu, and later we have shown that that may be the case because expected value of mu is expected value of Xbar is equal to mu, and variance of Xbar is much smaller than variance of the random variable. Yet still note that these will not show, let me put it that way, reveal why we started with Xbar at the very beginning. Maybe somebody has told us and we checked it, it seems to work, but still that's not a proof that Xbar is the best one, or that's not, that doesn't show how we came up with Xbar at the very beginning. I'm going to leave this to the very end, and I'm going to probably in the next lecture, and I'm going to just very briefly talk about that because that's a little bit of a deep topic. So for this case, the question is, how can we relate x1 bar and x2 bar to mu1 minus mu2? Again, without any indication or any root of how we come up with the relation, using our heuristics, if there is such a direct relation between those two, we may maybe come up with such a statistic. Since x bar is an estimator for mu, seems to be a good estimator for mu, why not use the sample mean difference as an estimator for this function? So our estimator is going to be defined in this way. Again, the first step of how to come up with an estimator with a convenient statistic is a question mark. But this time we use our heuristics, and let's say that d is equal to x1 bar minus x2. This is a statistic and also an estimator for mu1 minus mu2. Actually, I should put a question mark here because this is obviously a statistic because it's a function of two functions. But is it a good or convenient statistic for mu1 minus mu2? It is very easy to check that. We are going to do the same thing we have done previously. We are going to find the expected value of d. Expected value of d is going to be equal to expected value x1 bar minus x2. Since expectation operator is a linear operator, we can write this, and this is going to be mu1 minus mu2. And the first check is, okay, expected value of d, the statistic that we want to be an estimator for mu1 minus mu2, is indeed its expected value is equal to mu1 minus mu2. That's great. What about the variance of d? It's going to be variance of x1 minus of variance of x2. Now, the important thing is that although I said nothing about these populations, it says here in the normal, but just leave it here. If I just omit the normal assumption here, still I need to make the assumption that they should be independent. So two independent assumptions, two factors irrespective of each other. In this case, this is going to be equal to variance of x1 bar plus variance of x2 bar. Because 2 plus covariance x1 bar, x2 bar, this is going to be equal to 0 since they are independent from each other. Another point, minus sign here, the deviation, the difference between those two turns into a plus sign. Go back to the end of lecture 5, I guess. Here I talked about why error always increases. Even you subtract two random variables, the variance uncertainty in the final quantity is going to increase it, and that's a very good representation or demonstration of that. So variance of x1 bar is going to be population variance of the first population divided by sample size 1, and this is going to be n2. So basically, if we have large n1 and n2 values, this is going to be a small value compared to sigma 1 square and sigma 2 square. And here this says this. So therefore, we don't seem to have a large variance, and that shows that, at least that hints that D can be a good statistic here, and a convenient statistic here. So just like x1 bar is used for estimating a single population mean, x1 bar minus x2 bar or vice versa can be used to estimate population mean or difference between two population mean values.